English now. That is great. Oh, sure. So, welcome everyone back to the Addendum podcast. So this time we're doing something a bit new. So we've always been trying to expand to kind of like science fields, but this time we are actually doing it. So today we have Professor Rogers with us. So if you'd like to introduce yourself to us.
Sure. So I'm Dr. Patrick Rogers, so physics prof here at Marianopolis. I've been here for 7 or 8 years. I'm starting to lose track. It's been long enough.
Yes. So what are you interested in mostly in this wide field of physics, like before you came to teach at Marianopolis? And how and why did you become like super interested in this aspect of physics?
Sure. So like as a kid, I was a bit of a keener, I liked dinosaurs for a long time when I was like in elementary school. And then I, started reading books, seeing stuff, astronomy. I read a lot of Carl Sagan stuff, if you know, like Cosmos, Neil deGrasse Tyson. Yes. Carl Sagan was the guy kind of who started that stuff off. I got into like astronomy and science in general. In high school, I really liked chemistry, and then I realized what I liked in chemistry was actually the physics stuff, in terms of orbitals and, the quantum stuff. So I read those, I read A Brief History of Time and all those, those books for lay people in terms of science. And when it came time to go to university, I'm from Moncton originally, and in Halifax there's a University St. Mary's where they have like an astronomy undergrad, so an astrophysics undergrad. So I decided to give that a shot, and then that kind of got me into actually doing astronomy and research and everything. So I did some undergrad research with some profs right out of like my second year, my third year, doing research, and then I kind of liked that, wanted to go further, went into grad school where I did a master's which went into a PhD, and I was looking at planet formation, which is still a hot topic, but it was even more kind of new back then, so it was definitely like a field of growth, and I was interested in kind of doing computer simulations, so basically doing like little experiments, trying to like create baby planets, etc. on supercomputers and kind of working in that stuff. So that was my PhD research, which I did about 10 years ago now is when I finished. And since then, I haven't done any research or anything, but I spent 6 years kind of like doing science. I really wanted to do some active research, and now I'm happy to be here teaching and enjoying this kind of job.
Yeah, that sounds really cool. So you said that you were working on planet formation. So could you please run us through like the general process of it and how that works? Because like I know the general gist of like rocks smushed together, but what is the physics that's happening behind that?
Sure. You start off, planet formation starts off with the formation of a star. So you picture a big clump of gas and dust, which has kind of come together through gravity, and gravity pulls all that stuff down. Now, there's all sorts of motion in the galaxy. Things are kind of churned up. And so this stuff isn't just kind of sitting still and then pulled together by gravity, but there's a little bit of motion there. And so kind of like a figure skater with the arms out, when they pull the arms in, as gravity pulls all this stuff in, it starts to spin faster and faster. So when you form this star, you also form a disk of gas and dust around the star. And part of that actually goes into kind of feeding the star and making the star grow in the early part. But it's also basically the nursery where you get planets forming. So the typical kind of picture of how this happens, it depends on the type of planet. We have like small rocky planets like the Earth. You have Jupiter, which are mostly gas with a small kind of rocky core. And those mechanisms of forming are related, but a little bit different. For something like a Jupiter, which is kind of more the stuff I was interested in, basically you have to start off with little tiny dust grains, and they need to stick together. And then they stick together more and more. You get bigger boulders. They hit each other. There's lots of chaotic motion, etc. But they need to grow. And then once they're big enough, gravity can pull more of them together. And then you can start to build something that's looking like an Earth, a big rocky thing. And if it's pretty early, if there's still lots of that gas around in that disk, then once you build something rocky, something big enough, it can then suck up the gas around it and grow into something like a gas giant like Jupiter.
like how does it suck up the gas? Is it like attraction?
Gravity. Yeah.
Gravity?
Gravity's really the thing at play there. That's
Wow.
doing the sucking. Yeah, the sucking up. So you can take away, yes, the gravity sucks. So you can.
Okay, and you said something about protostellar disks. So why is it like a disk? Is it like actually flat, or is it like a whole plane, or like?
Sure. Yeah. It's not. It's pretty thin, generally, and it's because of that spinning. So as the stuff collapses down, it spins and it forms a disk because of angular momentum, which you can see in the mechanics class. But it's due to that spinning. And basically, to get the stuff to actually fall in the star, you need some sort of friction for stuff to like lose energy, etc., and fall in. So stuff is kind of happy to be in that flattened picture, kind of like a pancake rotating around, except stuff closer to the star rotates faster than the stuff farther away. So it's not like a uniform, like a record perfectly, but that gives you a bit of a sense if you think of like a record just going around. It's fairly flat, but it does have some thickness.
Okay, that's pretty cool. Is it so like? Are there certain spots in like this big pool of gas where like stars are more likely to form, or where planets are more likely to form? Because you also see those rings that still exist around planets like Jupiter or like Saturn, right? So is it remnant of that?
Yeah, essentially. So you can the star forms and you have this disk going around. Planets form out of that. Once planets start to form too, they'll interact with that disk. And you will get the rings and gaps in the disk and all sorts of cool features, which kind of in the last 10 years or so, there's been telescopes which have been able to actually basically take pictures of these disks. And you see all sorts of features where it's the planets doing stuff to that disk, interacting. And when you get individual planets forming, it kind of scales down again where the planet forms with gravity pulling stuff in, and you can also you expect to find kind of little disks going around there where you could get moons forming, etc. And yeah, so you can kind of have the process kind of repeating on that level too. And in terms of what's happening in the disk, once the star kind of turns on, closer to the star, it's hotter. So you don't have things like ice close in. And that makes it harder to build a planet with a lot of ice, etc., with where the Earth is. So that's why we have rocky planets closer in, and farther out you get these bigger things which will have a lot of ice. And if they can get big enough, like I said, suck up that gas, become giant planets.
I see. That's pretty cool. And people talk about a Goldilocks zone when they're looking for exoplanets. So what is this Goldilocks zone? How does it happen? Are there other conditions that help it become a Goldilocks zone other than just distance from the star? Is there a certain type of gas in there?
Sure.
Water?
Yeah, so Goldilocks, when you think about why we're looking at other planets, etc., my research wasn't looking specifically at finding planets like the Earth. I was more focused on the bigger Jupiter type things. But of course, when we're finding other planets around other stars, we of course want to ask, well, are there life forms on those planets? And well, we have one data point here where we have life, and that requires liquid water. And so there's a habitable zone. If you're too close to the star, it's too hot. You're not going to have liquid water. If you're too far away, it's too cold. It's going to be ice. So that Goldilocks zone is going to be where you can have a planet in what's called the habitable zone, but where you think you could have liquid water. That'll depend on the distance from the star. That's clearly going to play a role. Even then, it'll depend on the planet itself, because on Earth, we talk about climate change and greenhouse effect and all that, but we do need some greenhouse effect to kind of keep things warm enough here to actually keep liquid water as well. You just don't want too much of one. It can end up like Venus, where it's just inhospitable. So that's where the Goldilocks zone kind of thing would come in. So people are looking, definitely looking at trying to find Earth analogs going around other stars. When I was a kid, we only had 8 planets. well, we had 9. We had Pluto. We kind of get him off. But now, I just checked the website now. Now we've actually observed 5,000 planets around other stars. And it's kind of hard to find the ones that are closest to Earth, or most like Earth, just because they're small. So it's harder to find small planets just because, well, they're less big. They have less of an effect. They're harder to kind of see. But we've found planets that are around Earth mass, that kind of a little bit bigger, super Earths, that sort of thing. So it's it's definitely an exciting time where we're starting to find these types of planets.
Yeah. Also, there's a difference in the atmospheres for different planets, right? Or no, yes, no. Like for Earth, I think the gas that is most present is like nitrogen and oxygen. But for a planet like Jupiter, I think it's methane. So what causes this difference? Because in the beginning, wouldn't that have been like a kind of uniform distribution of like all sorts of different gases? So how did it come to be that like a certain planet would have an atmosphere more predominant in one gas compared to like another?
Sure. Yeah, there's some interesting stuff there. It depends on your location in the disk. So if you're closer to the star, it's hotter. It's harder to hold on to like lighter elements. Also, as the planet's forming from kind of asteroids and that sort of thing, if it's cold, there's going to be a lot of like water ice there that gets built into the planet. So it's going to depend a lot on kind of where you are, and it's also going to depend on the mass of the planet. So if they can kind of hold on to their atmosphere as well. So something like Mars, less massive than the Earth, also had a lot of like we can even then go in. It depends on the magnetic field of the planet, because that'll help protect from the effect of the star. So there's lots of things that go in there. But the first thing would be kind of your real estate, your location, and then also the size of the planet would go in there. Now, one thing they've started to do it with the James Webb Space Telescope, which is now up in space, and they're kind of getting that ready to go. They're actually trying to measure the atmospheres of planets going around other stars. So kind of like in the WAVES lab, the last WAVES lab you look at hot gas and you look at the spectral lines, so the light that's emitted by one type of element. And students always have fun. We give them one unknown gas and they try to figure out what type of gas it is by looking at the light it emits. You can do the same kind of thing with the light coming from other planets. So you try to look for those kind of chemical fingerprints, those signatures, to see what kind of atmospheres they might have. And there's the hope there that you can look for chemicals that might be in the atmosphere, but kind of a product of actually having life on that planet. So some kind of non-equilibrium chemistry stuff. So that might be one way of actually finding life around on a planet around another star, at least the first kind of signs of life.
I heard, this is straying a bit from planet formation, but I heard that some astrobiologists,
there you go.
they're looking, because for humans right now on planet Earth, most of us were like carbon and water-based forms, right? But then, is it possible that like we could have a different basis of life based on like the elements? Because carbon and water are special because of, the electronegativity and how carbon is able to make a lot of bonds and all that. But is it possible then that in another planet that we could have like a different basis of life?
That's a really good question. I remember there's the original Star Trek. I remember there's an episode where they find like a silicate-based life form, and it talks exactly about that. And that's a question I honestly have no idea. Good question that maybe somebody in biology or chemistry would be better suited. There are definitely astrobiologists, who kind of looking at interesting questions like this. Whenever we're looking for, life or intelligence or anything, of course, we only have this one data point, which is the Earth. So, of course, we're going to be looking for something similar. So, is something else possible? I haven't taken biology in recently enough to give you any kind of good answer on that. But, there is always the idea of, we're looking for things very similar to us. Is there a possibility for something to be different? Maybe another follow-up podcast with somebody who would have some ideas on that.
Probably, yeah. Okay, so we're gonna rewind a little bit, and you talk about how electromagnetic forces could protect the planet's atmosphere. Was that it?
Yeah.
The planet's atmosphere from the sun's radiation. So, first, how does that work out? And then, why is it important that the atmosphere isn't exposed to like the sun's radiation? Like, what does that do to the planet's atmosphere then?
Sure. So you have high energy particles that are coming in from the sun, and they can basically, knock stuff out of the atmosphere. So that can like get rid of stuff in the atmosphere. And the magnetic field, well, these particles coming from the sun are charged, and so the Earth has a magnetic field because of its like molten core, and so that magnetic field, what it does, as you'll find out when we get a little farther in E&M, but basically when you have a moving charged particle, it's going to interact with that field. And so the field doesn't allow those particles to kind of come right into the atmosphere. What it does is it's going to, it will kind of trap them, certain areas, certain amounts, and then funnel some of them in towards the poles, and that's actually where you get the northern lights and the southern lights. So you kind of see that nice colorful phenomenon, but it's actually in that process, that magnetic field is protecting us and the atmosphere.
So
let me just pause for 1 second.
yes.
I'm not going to be available during AP, unfortunately.
Okay, thank you for telling me. Bye.
Yeah.
Yeah.
We can
Okay.
edit that out.
Yeah.
Well, we can keep going there.
Yeah. So, do planets, when they form, do they just automatically have an electromagnetic field, or is that specific to only certain planets?
So you'll need you need a molten core. So you need that motion. So you need like the iron in the center of the Earth is able to flow around. Now planets, when they form, they're really hot because you're collapsing asteroids and all of those planetesimal little bits that make up the planet together. There's a lot of energy there. So they're very warm and they cool. And they cool, their outsides get hard, you get a crust. And then if they keep some of that warm from the inside, there's also radioactive decay, which helps there as well. But you can keep that inner part fluid, and as that moves around, basically you have moving charge, and that's what creates a magnetic field. So what you need on the inside of a planet is that molten core to be able to produce that magnetic field. So something like Mars is smaller than the Earth, a fair amount smaller, so it just is able to cool off quicker. Just like if you, run a bath compared to like pour some hot water in a cup of tea. The tea is going to cool off faster, surface area, volume, that sort of thing. It's going to cool off faster than the bath. So the same thing with planets. So Mars, at some point, basically lost its magnetic field because it's just smaller, so it cooled off more quickly.
Yes. So is there like a reason why certain planets will be bigger than others, or is it just completely random that Jupiter is something big that's like way out there, and like all the smaller planets are kind of like shoved more towards the sun?
Yeah, no, that's a great question, and what people like. I was working on that sort of thing. People are still working on that sort of thing. One of the interesting things, we had back when I was a kid, we had our solar system. Those were the planets we knew about. Once we started detecting planets around other stars, we saw that other solar systems there's a whole variety of types of solar systems. So there are solar systems where you have big planets like Jupiter, even more massive, that are really, really close to their star. So closer than Mercury is. And so the idea, and everything I'm saying here is dated a bit by 10 years. I haven't looked at the most recent research, so I'll put that qualifier in. But, these were things which were not expected. And so do the planets, how do they form there if it's so hot and the planet can't hold on, it can't hold on to that gas because it's too hot there? Do they form farther out and then migrate inwards? It turns out, if you look at the physical theory and computer simulations and that sort of thing, that once you form something in a disk, it interacts a lot with the disk. So you make a new planet in a disk and then it starts interacting, and so it doesn't necessarily stay put. It can move in. So you can get planets moving around. They can interact with each other too. They can move out. They can get flung out of the solar system. And yeah, so there's a whole kind of variety of different types of solar systems that get formed, and kind of the job of an astrophysicist is to try to understand, well, in that system, what made the Jupiter be really, really close, whereas in like our solar system, it was able to stay reasonably far away. They discovered a few kind of interest to what I was doing is they discovered a few of these Jupiter-type planets really far away from their stars too. So we're at 1 AU, an astronomical unit, 1 unit away from the sun, so the Earth. Jupiter's at like 5, if I remember. Pluto, those guys are out around 40. Well, they were finding planets bigger than Jupiter at 100 times that distance away from their star. And so they were finding those there. I haven't checked recently. It's not that those are always the most common, but there were situations which were coming up. So you want to ask, well, how did that work out? Did they get formed there? Did they get thrown out there due to interactions with like the disk or with other planets? Or when these stars are forming, they're not just necessarily by themselves either. There's stars forming around, or there interactions there. But yeah, so there's the question of why do planets end up where they are is one that's full of kind of different mechanisms and different complexity, and is definitely a current topic of research. And people are trying to figure out, what types of solar systems are out there and how did they get like that.
Yeah. So when you say about like types of solar systems, is there like a classification method, or is it just like where the planets form and how this causes like the things inside that solar system to interact with each other?
Yeah, so this would be based on observations.
Mm-hmm.
So I think there's like 3,000 different systems. That might be one planet, that might be multiple, but they definitely do find like lots of multiple planet systems. And so it's based on observations, and it's just kind of, you find a big variety. So you can classify them in certain types, but it's not that like our solar system is just typical of everything that's out there. So our observations too are limited in how we see these planets, so it would be hard to find things like the Earth, and easier to find big Jupiter-type planets close to their star, just because they have more of an effect. There are different ways of finding planets too. Basically, the Jupiter ones were first found by actually looking at how much the planet's gravity tugs on the star. And basically, if you remember the Doppler effect from waves, do the same thing for light, and that comes in. Other ways of finding planets are, you have a planet that goes around the star, and if you're looking, if the angle is just right, the planet can pass in front of the star. And the star will it's like a mini eclipse. It'll just dim a little bit. So that's how a lot of the planets were discovered, with that kind of mini eclipse method. With the Kepler Space Telescope, which was put up, and that discovered thousands of these types of planets. And it was akin, I think the analogy is, if you have all the lights on in the Empire State Building, and if somebody puts the blind down by 2 centimeters or so, that's the type of variation that this telescope could find.
That's like really tiny, and this is at like how far of a distance?
Pretty far. Let me put it that I don't remember the exact numbers, but
God.
we're in our part of the galaxy, but these stars are far apart. And so so for that type, when you're looking at this dimming, well, dimming once could be anything, but what you want to do is see it dim, every year or something, so you can see some periodicity. But then that limits, if you have planets out at 100 AU, they take many years to go around, so you'd never find those ones that way. There are those planets that were really, really far away, you can actually see directly, because they're young and very hot, you can basically see the light that they're giving off, because they're far away from the star. So picture like trying to see a firefly beside like a big spotlight.
Mm-hmm.
That's kind of the idea, is that the star is really bright and the planet is really dim, and you're trying to find that really dim thing near the spotlight. So that can be hard. So the ones that are farther out make it easier to see that. So we've got different ways of finding these planets, and they're they test kind of different configurations of where these planets are in that. But there are definitely biases, and that we know a lot about. We know a lot more about what types of planets are out there, but we don't know about everything. Definitely, there's definitely gaps in the knowledge there. But yeah, so those are like where we get the ideas of what types of solar systems, what types of planets are out there, and then you go and talk to theoretical astrophysicists and people who do computer models and that sort of thing, and they try to figure out how those get made.
I see. So part of your research was also like incorporating these models into a computer, right? So how nice was it to incorporate laws of physics into a computer, given like the context of like a humongous solar system also?
Yeah, so I mean, computer modeling is a very important part of astronomy. So in astronomy, you have of course, another important, maybe more important thing is actually looking through telescopes and seeing what's out there. Those people are dealing with computers all the time too, because just the amount of data that comes in from those, they have to do all sorts of analysis. So that's one type of like computing in astronomy. There are also kind of pen and paper theory people who try to work things out, but that can be hard. You can make certain kind of progress on questions that way, and it's important, but you'll have to make all sorts of approximations, and you can get a certain distance, a certain progress with that understanding. But in order to get further, basically what's done a lot is you try to make a little experiment. In astronomy, things take millions or billions of years, and they occur on vast time scales. So you can't like set up a lab to like make a planet. So what we do is we try to get physics into like a computer code, so that we can kind of have a little lab there where we can test out these ideas and see what works and what doesn't. Now, in that, we have to put the physics into the computer code, and that's a challenge. I was talking with my mechanics students this week, and we were doing projectile motion. They're like, oh, well, why don't we do air resistance? And it's like, well, that starts to get hard, and you need to do a bit of computer modeling to actually work out the details. And so that's going on like just at that very basic level when you're trying to simulate, the formation of a solar system. You have to make all sorts of approximations as well, because even with the world's best computers, to get anywhere with it, you're trying to approximate the physics. And you want to do the best job you can at approximating it and include all the physics that you need to, but you have to be clever about it, because otherwise it just becomes completely intractable. Computers are really fast, but there's a lot of complexity to what's going on. So what I was working on, I had an interest in, there are people who take these codes, they're built by different groups, etc. And there are people who primarily kind of take them and they run the experiments and then see what happens, analyze stuff. I was interested in actually working on writing the code as well, putting new physics in. And that's what led me to McMaster, where I did my PhD. And so I was able to work on this relatively large code, which did gravity in a clever way. And it also did the gas physics in a clever way. It kind of, you were modeling what happened with the gas physics by kind of treating it as a bunch of little drops. Droplets. You can think about it that way. And so you break this disk, this protostellar disk, into like a bunch of little droplets, and you watch where the droplets go. And the nice thing about that is when you like have this region of collapse, so gravity's pulling stuff together, etc., is that's where the droplets go. So that's kind of where your information goes. So it's a good way of modeling this. So I was working on, it had gravity, it had gas physics, it had all sorts of different stuff. It's internationally used, that sort of thing. So I was working on putting basically what's called radiative transfer, but the heating and cooling into this. So what happens, so I talked about planet formation, this building from dust grains, building rocky things and building up from there. I was actually looking at a different way of making planets, kind of the less orthodox idea, in that as the star gets made and this disk is around the star, feeding the star, if the disk is really heavy, it can become unstable. Basically, it just has too much gravity going on. And so what happens there is the gravity dominates, and it can just have regions which will collapse into maybe big things like Jupiter really, really quickly. So this was an idea that was been around for a little while, and different groups were working on this and seeing whether this was like a plausible way of making things like Jupiter or some of these other planets that have been discovered around other stars. Now in that process, so if you kind of start off the experiment with a nice smooth disk going around the star, if it's massive, it'll create nice spiral arms relatively quickly. And what I was looking at is, okay, can these spiral arms basically break? Can they collapse and form something like Jupiter really, really quickly? So that process could take like tens of thousands of years compared to kind of millions of years of building up from dust grains. So kind of an alternative way. But of course, if you're going to collapse the stuff down, gravity pulls all it in, well, there's a lot of heat that gets generated. And that acts to keep the stuff puffed up. And so that prevents the formation of the planet. So what you need is enough gravity to want to pull stuff in, but you also need it to be able to cool so that it can actually collapse. Otherwise, what happens is this stuff is spinning around in this disk, but it's not all spinning at the same rate.
Yeah.
So if you start to collapse something, but it doesn't collapse fast enough, it gets torn apart. So you want to, so you have to work out how fast it needs to cool to be able to collapse down, and lots of work was done on that previously. And kind of when I jumped into things, different groups, I was not the only one doing this kind of thing, but different groups were trying to model this, and one of the issues was they were getting different answers. Using different computer methods, etc. But yeah, it's hard. You're making approximations, doing the best that you can, but people were kind of getting yes, and others were getting no, and so it was a debate. So I kind of jumped in this debate, did some work. I didn't settle the debate by any means, but I kind of pushed it along in the direction that making something like Jupiter in our solar system is probably the dust grains that build up. It's probably not this way, just because it doesn't cool fast enough. Maybe for some of the stuff that's farther out, this might be a mechanism. But if you were betting your money on it, it's probably on the dust grains building up for most of these types of planets. But there's still room for this, what's called gravitational instability, where this gravity really kicks in and collapses stuff down really, really quickly. In the formation of the star, this disk. But it has to happen when the disk is really, really massive, which would mean really kind of early in the process. It has to happen kind of far out so that stuff can cool fast enough.
So maybe that's why you have like the big giant planets at the edge of the solar system, maybe?
That was kind of one of the ideas there too. Now, in the work that I was doing, and of course there's lots of uncertainties in all of this stuff, but you need to get even farther out. So what I was looking at is it kind of becomes plausible maybe out at around 40 AU, which is like where we have Pluto. So it's not doing anything to like create our solar system necessarily, the planets in our solar system. Then again, if you form these things in the disk, they interact with the disk, so they might migrate. And so there's there's still ideas that I'd say this scenario is probably less plausible, but it's certainly not ruled out at all that things form farther out and then move in. But it would definitely not be the consensus view. But there's enough uncertainty in all of this that there's still open possibilities. It's not a part of science where it's really just like you do one study and that really rules something out completely. There's still enough complexity and unknowns in the observations and that there are open doors, but as more and more groups do research, it pushes things in one direction.
I see. So does that mean that if planets do interact with each other, are the orbits of some of the planets in our solar system also being shifted? No. Yes.
Yeah. So this happens early on, too. It happens more then, just because as these planets form, there's still lots of debris left around, and so there are lots of these other planetesimals, rocky things, etc., for them to interact with. And in the models of like our own solar system formation, things don't necessarily form exactly where they are now, but they do move around. And Jupiter's the biggest thing by far in our solar system, in terms of planets, and so it kind of has a dominant role in that process. So as it interacts with stuff, all sorts of things will get thrown out. There'll be migration. You can expect migration in and out and that sort of thing. So that was definitely expected as in the early solar system for this type of thing. Now the solar system is pretty clean. Most of that debris has been interacted or thrown out. There's the asteroid belt, which is basically leftover debris, but it's at a spot where it's kind of in a stable spot. So once you throw enough stuff out, things settle down a little bit. But even the formation of our own moon, the idea behind that is that early on, something like the size of Mars came and smacked into the Earth. And the moon was basically kind of the leftovers that got shot into space. And that's backed up by actually the same kind of computer models I was doing, that same technique, and evidence in terms of the composition of the moon and what it's kind of made of. Looks a lot like the outer part of the Earth. So the history, the early part of the solar system was very violent. Yes. You see the moon, you see all the craters, etc. There's lots of action. It's a quieter time now.
Yes. So, so why should we care about planets in the first place? It's cool, and the physics behind it is super interesting, and the joy of being able to understand the universe is great, but there's always people out there who are like, why should we fund the NASA research? Why should we look out to space when we have problems here on Earth? So what's going on here?
Sure, yeah. I think I would say you just answered the question kind of for me, in that it's cool. We should, understanding what the universe is like is a goal in its own. And there are people working on very small details and sorts of in science and that sort of thing. I think of friends I did my PhD with, but which I found that they were doing less interesting, but they were just really interested in solving these problems, figuring out what the nature of the universe is, for the sake of knowing. I think that's worth it in its own. Now, in terms of astronomy and that, people are interested. There's definitely an interest in this type of stuff, and I think it speaks to there's kind of a philosophical side of what is our place in the universe? How does that fit in? With this planet stuff, where do we come from? What's the whole process? Those big questions. With the planet stuff, that's, there's the possibility of figuring out life around other planets, which, that's questions don't get much bigger than that. In terms of, figuring out, there are planets around other stars. Some of them look like Earth. We can start to measure their atmospheres. Do they look like the Earth's atmosphere? Can we see biosignatures, etc.? That answering that type of question, I think, is huge and well worth the money. A lot of dollars are spent on space telescopes and that sort of thing, but when you compare to the amount of money that's spent on other things, it might not be that crazy. So I would put it in those more philosophical terms rather than I don't know, some sort of economic output or something. But whenever you're doing pure science, you're discovering things. You don't know where that will lead either. These types of computer simulations, etc. They're used in all sorts of other fields. The same kind of modeling of fluids and that is used at steel companies to model the molten steel pouring into molds and that sort of thing. So you can take these ideas and actually do useful things with them as well, but that's definitely not why I got into it. It's more of these big kind of questions of what's out there in the universe, how does where does that come from, are we alone, those sorts of things.
Cool. This is kind of like a PS then. So the universe is expanding, but what is it expanding into? And is it just gases that's being pushed out there? How long should we expect to have new planets form out there? what's going on at the edge of the universe?
Sure. Yeah, that type of big picture stuff, less my expertise, but in terms of like the Big Bang and that, yeah, it's that everything is expanding. So space itself is expanding as well. So it's not like expanding into something, it's actually everything is stretching and expanding outwards. And it's all very good evidence for that. It fits very well with our models and that. Yeah, it's weird. Expansion is speeding up, it's accelerating. There's a Nobel Prize about that fairly recently. What's causing that acceleration? That looks like it's a whole big unknown. Like 70% of the energy in the universe is something we just don't really know what it is at all. Lots of big questions there. Now that's happening at the biggest scale. So on these smaller scales, like even our galaxy, which is pretty big, something like 300,000 light years across. But there, the gravity of the galaxies is basically keeping stuff together. So I don't notice that you're part of an expanding universe. I mean, there's no expansion there that I can tell of. Because we're close enough, the gravity is kind of taking over there and keeping things constrained. So in terms of like star formation, planet formation, that sort of stuff, that stuff's all still going around. The galaxy's a very dynamic place in terms of the motion of the spiral arms in the galaxies and gas coming in, compressing in those arms, supernova, stars dying, blowing up, pushing gas into each other. It's definitely something where there's a lot of movement and a lot of action. So that's definitely still going to be going on for a while. The time scales here are, of course, much longer than any of our lifetimes. So we don't, it'll be going on for long enough for more people to go do PhDs in astronomy and then study this stuff. One interesting thing about astronomy, of course, is that you can look back as you look farther away. With telescopes, you look further back in time too, so you can actually see how star formation and that is all working at earlier times in the universe as well, just by looking at galaxies that are farther away. There's all sorts of crazy stuff as the galaxies collide with each other too. That happens, and then there's more star formation. There's all sorts of crazy stuff that we see observationally, and we model in terms of computer simulations. The same code I was using was used for galaxy formation, so looking at how galaxies build up from basically smaller galaxies colliding with each other and looking at the details of that. So there'll be lots going on. If anyone's interested in studying astronomy, there's lots of stuff to learn, lots of big unknown questions, and lots of stuff to continue with.
So do galaxies ever? Wait, does that mean is it possible that all the galaxies would just collide eventually, but the fabric of the universe is still stretching, and it's one humongous galaxy in a continually stretching universe? How does this work out with gravity and all of those things?
Well, if you look at the large enough scale, stuff is spread out enough that it's not all going to collapse to one thing, because there's stuff tugging, but there's not a center, so it's not like everything's falling towards one spot. It's tugging on each other. So actually on the large scale, you get this kind of filamentary web-like structure. You can Google it. It looks pretty cool. You can see this from telescopes and from computer simulations of this. But certainly within clusters of galaxies and that sort of thing, that is essentially how we think galaxies get bigger. Is you start off with smaller kind of galaxies and they collide and build up, and you do get really, really big ones as well. But you don't have to worry about all of the universe falling into one kind of spot.
Okay, so I guess we'll end there with the fate of the universe kind of up in question. Will we collapse together? Will we spread far apart? We don't know. But thank you so much for doing this interview. This is gonna be the first science interview on Addendum, so I'm really glad that you were able to help us out with it. But yes, that's it. Thank you.
Perfect. Thanks for having me. It's been fun.
Yes.